In this video, I'd like to talk about higher order derivatives, concavity, and then also the second derivative test. The first thing is understanding notation for higher derivatives. So here, the second derivative we indicate by saying f double prime of x. Or another way to say that is the notation next to that is you see the d with what looks like an exponent of 2 and then the y. And then into the denominator of that, you have the d and then the x and what looks like a power of 2. That essentially reads it's the second derivative of y and then with respect to x in that particular notation. You can also, I'm going to say for, let's say the third derivative. If you want to take a third derivative, you can use similar notation as far as the primes. So you could say f triple prime of x. And I'm going to say another way to do that is you could say the third derivative of x. And so we sometimes get tired of doing all the primes. And so for the nth derivative, you'll sometimes see the notation f, and then it looks like an n power. That's not really what it is. It's just giving the notation for that higher order derivative. So what I want to look at first is seeing what higher order derivatives look like and how to evaluate them. So on here, it's asking me to find the second derivative in general terms of x, and then also evaluate the second derivative at 4 for each of the following. So this first one we notice is a nice polynomial function. So the first thing you're going to do is find the first derivative. So f prime of x in this particular function, we're just using a power rule. And so that would become 3x squared, and then plus 8x, and then derivative of 2 is just 0. So there's the first derivative. And literally to take the second derivative, it means take the derivative of the first derivative. And so from there, we're now treating this like a new function, and we're taking its derivative. So we'll say second derivative would then be, we're looking at a nice polynomial function. Once again, we're using power rules. So the derivative of the first derivative is 6x plus 8. Okay, so there's the second derivative in terms of just x's. Okay, they also wanted us to find the second derivative evaluated at 4. So we would do second derivative evaluated at 4 and simply plug in 4 everywhere there was an x in the function. So we'd do 6 times 4 plus the 8. And so on there we'd end up with 24 plus 8. And then that would yield 32 out. So the second derivative evaluated at 4 is 32. All right, for the next function down, we see that that's a root function. We know to take a derivative, we want to rewrite the root as a fractional power. So on this one, we would say 3x plus 4. And then that's going to be raised to the 1/2 power. All right, then to take a derivative, this is going to have to be a power rule followed by a chain rule. So the 1/2 is going to get multiplied to the front. The 3x plus 4 would stay. And then that 1/2 power that I had originally would need to be 1/2 minus 1, so reduced by 1. So that would be negative 1/2. And then I would take the derivative of the inside portion. So that would be 3. All right, now on this particular one, if my ultimate goal is to find a second derivative, I don't always simplify the first derivative as I would. What I would normally do to simplify this first derivative would be to get rid of negative powers. But because I know I'm going to need to take another derivative, I'm not going to get rid of negative powers. I'm going to leave them as they are, because with them as they are, I'm going to say they're kind of geared up to do a power rule on. What I am going to do is I have the 1/2 at the front and the 3 at the back. I'm going to go ahead and multiply those values. So I'll have the 3/2, and then I'm going to leave this as a 3x plus 4 raised to the negative 1/2 so that I'm able to take the derivative of that function now. All right, so now I take this and I say, hey, to go on to the second derivative, I'm now looking at that as my new function. This, I'd have to use the power rule followed by the chain rule. So I'd multiply the negative 1/2 to the front, multiply it by that 3/2. I'd keep the 3x plus 4 that I had on the inside, and then I would reduce that power of -1/2 by 1, so it would become -3/2, and then multiply by the derivative of the inside, which would be 3. Now, at this point, when you get to the second derivative, you now want to reduce this as much as you can by getting rid of negative exponents and combining things together. Notice here we can write that 3/1. Fraction-wise, we have a -1 times a 3 times a 3. That could be a -9. And then in the bottom, we have a 2 times a 2 times a 1, so that'll be 4. And then what I'm going to do is kind of steal this fraction and say, hey, this 3x plus 4 would now be written down in the denominator, and it would be raised to the 3/2 power. If you wanted to give that as your final answer for your second derivative, you could, or if you would rather write it as a, I'm going to say type of root, you could do that as well. So you could do that, or you could do here square root, and then it would be 3x plus 4 all to the third. All right, and that third power, it can go either on the inside of the root or the outside, either way, but either one of those would be fine. I'm actually going to use that second version for my derivative that I'm going to plug into, just because it's an easier thing to think about as far as evaluating. And so now if I go on and say I'd also like to find f double prime at 4, then I'm going to substitute 4 in anywhere there was an x in that derivative. So it'd be -9, and then all over 4. And then that's going to be a square root of 3x, but it'll be 3 times 4, and then plus 4. And remember, we said we can either write the cube on the outside or the inside. I'm going to go ahead and write it on the outside. I suspect that's going to be where we want to use it. So in this simplification, we'll have -9 on the top, and then over 4. And then underneath that root, we have 3 times 4, which is 12, and then 12 plus 4 is 16. So you're really taking the square root of 16, and then when I'm done taking the square root of 16, I'm going to cube that. It's easier to do that. In other words, if I say square root of 16, I know what the square root of 16 is. If the cube were underneath with the 16 right now, that would be indicating that we want to cube 16 first, and that's going to give me a much larger number. So I think order of operations here would be easier to do the root first, since it doesn't make a difference. So -9 over 4 times, and then square root of 16 is 4. And then that's going to be cubed. And then ultimately there in the bottom, we see that we're actually going to have 4 to the 4th because we have 4 multiplied by 4 cubed. And on that, I just type that in your calculator. So on that one, if you raise 4 to the 4th, you're going to get 256. So the value there of the second derivative at 4 is -9 over 256. All right, I'll also want to look at a second derivative in terms of an exponential function. On this particular example, what I'm going to do is I'm going to separate the constant out and then look at the inside part there. So to find the second derivative, I first need to find the first derivative. So the constant of 3, I don't have to involve in my derivative. The inside is an exponential function. To take the derivative of an exponential function, I take the natural log of its base. Well, its base is e, and I know natural log of e is 1. If you'd like to write that, you can. If not, at this point, you can leave that off. It's the exponential function itself, and then times the derivative of its exponent. On this one, the derivative of the exponent would end up being 8x. All right, from here, I'm going to go ahead and multiply any constants I have. So I have a 3 times an 8. I'll multiply those. And I'll also pull the x up front with those constants. So 3 times 8 would end up being 24. And then the x, and then e to the 4x all squared, or to the 4x squared. All right, now, from this point, when I'm looking at the second derivative, this is going to be more difficult. The 24 can be separated out, but now I have this extra x in here, which is going to mean that taking the second derivative is going to require a product rule. So we have the first and then the second in there. So on there, f double prime of x, The 24 we can keep out in the front, but then we're having to use product rule on the inside. So we're going to say first times derivative of the second, and be natural log of e, which is just 1, the exponential itself, so e to the 4x squared, and then derivative of the power, which is 8x, and then plus, keep the second, so e to the 4x squared, and then derivative of the first, derivative of x is just 1. Okay, so we have to be really careful there, and then we want to simplify this down. So on this particular one, see if we can factor anything out, and also we have possibly some things that can be multiplied together. We notice that both of these terms have an e to the 4x squared in common, so we're going to factor that to the outside with the 24. All right, also notice we have this x and this 8x. Those need to be multiplied, so we're going to have 8x squared. And then factoring an e out of this group, that leaves us only with that 1, so we'll have plus 1 there. And it looks like that's factored completely. So there's the second derivative, just in general terms of x. Okay, and then on this one, evaluating that specifically at 4, I would say f double prime evaluated at x equals 4 would equal 24 e to the 4 times 4 squared, and then times 8 times 4 squared plus 1. All right, what I'll do first is I'll do the exponent, and then I'll do the inside group that's in the brackets. So 24. This will basically be 4 times 4 times 4, so it'll be 4 cubed. So on there we need 4 times 4 is 16, and then 16 times an extra 4. That will give us 64. So the new power there is 64. And then over here, this looks like 8 times 16. So if we did some scratch work over on the side there, that would be 128. And then 128 times 1 is going to be 129. All right, and then finally I'll multiply the 129 in the group by the 24 that's out in the front, and I should get 3,096, and then e is to the 64th. Okay, and feel free, I've done a little scratch work out to the side, but feel free to use your calculator on those type of calculations. All right, we've got a definition here. It says a point where the graph of a function has a tangent line and where the concavity changes is what we call a point of inflection. Well, first of all, what is concavity? Concavity basically means cupped upward or cupped downward behavior. And so if we have a change in that type of behavior, that's going to be what we call a point of inflection. An inflection point occurs at an x in the domain where the second derivative is 0 or where the second derivative does not exist, where it's undefined. This sounds vaguely familiar. When we did relative extrema and we were finding critical numbers, to find the critical numbers we found where the first derivative was 0 or where the first derivative was not defined. And then from there we did a number line test to determine if we had any kind of relative max or mins. Second derivatives tell us about specifically concavity, and like I mentioned before, that means either cupped up or cupped down. And then if concavity changes from one to the other, we have what's called this point of inflection. So on here, I want to look at this given a graph so that you can kind of see what we're talking about here as far as concavity. And I'm actually going to answer this question a little bit out of order. They're asking for concaved up and down as these bottom two pieces. So let me come over here and look at concavity first. So if we look at this graph, kind of from left to right, obviously this goes on to infinity. If we look here, all the way up, and it looks like until about 0, that's going to be what I consider concaved upward. So from here, and I'm going to kind of dot this out. This is not meant to be an asymptote, but there we're concaved upward. Then it looks like, and I'm going to change colors here so you can see, it looks like from here down to about this point somewhere, it's going to be what I consider concave downward. And I'm going to kind of dot this off just visually so you can see a concave downward type behavior. And then from this point, looks like on, up, and around, and looks like all the way up to the, I'm going to say infinite right side, we're now talking about concaved up. So that's what we mean about concaved up and down. So on this one, we would be concaved up from negative infinity, looks like all the way up to 0. And then union, looks like it starts concaved up again at 2. And this is just like increasing, decreasing. You always look at the x values. So from 2 on to infinity. And then concave downward, it looks like that's going to be between x is 0 and x is 2. So between 0 and 2, we have this concave down behavior. All right, now I'm going to go back and talk about something we've already talked about, and that is increasing, decreasing. That's different here as far as what I want to look at. Increasing means that my graph is going uphill. Decreasing means it's going downhill. And so in general, we can see from this part of the graph all the way down, 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 till it looks like about that value, we have, hey, this graph is going down. And then when I come over on this side, my graph is now going up. And we see the only value there of interest is that 3. So it looks like this guy is increasing from 3 to infinity. And it looks like it's decreasing from negative infinity all the way up to 3. Okay. We would call this value, looks like negative 27, a relative minimum because we changed from increasing to decreasing at that particular point. And then, I'm going to say based off of the new information we have, looks like 0, 0 is a point of inflection. That means that the concavity changed from one to the other. It looks like it was up on the left and down on the right. And then also it looks like we have this ordered pair. This ordered pair looks like 2 and negative 16. That's also a point where you have a concavity change. So that would be a point of inflection. Okay, so we're going to say observe points of inflection at, it looks like 0, 0, and that appears to be 2 and negative 16. It looks like up here some of my pen didn't write, so let's correct that word. Observe. All right. All right, so on here, what we're going to do is start a couple of problems kind of in what I would consider the middle of a problem. So on this one, they've given me the second derivative. They've given the second derivative in a really, really nice, I'm going to say factored form, and they've asked me to find where the graph of the original function, even though I don't know what the original function was, is concaved either up or down. So they're starting me at the point where they've already gotten that second derivative. And honestly, we don't care what the original function is, but we're able to tell behavior of the original function based off of this information. So find basically possible points of inflection. So we abbreviate that on here, possible points of inflection. So POI. All right, and possible points of inflection are going to occur either where the second derivative is equal to 0, or where the second derivative is undefined. All right, on this one, the second derivative would be 0 anywhere you have zeros for this factored format. So that would be where x minus 1 were 0, where x minus 3 were 0, or where x minus 5 were 0. So that would give me x is 1, x is 3, or possibly x is 5. All right, f prime being undefined, that wouldn't apply in this situation. If I did multiply all those factors back out, I'd have a polynomial function. So in this case, determining where f prime, double prime is undefined is not relevant. All right, so now what we do is we talk about concavity. To talk about concavity, we do a number line test, and we use these possible inflection points as the values that we test around. So this should feel familiar, but we're doing this with a different derivative, and these aren't critical numbers, these are possible points of inflection. So on here, we're going to put in order 1, and then 3, and then 5. I'm going to go ahead and dot these off. Those aren't asymptotes, we're just visually breaking up the graph. And then from here, we're going to pick test points. So I want something to the left of 1 that's going to be in my domain. On here, we don't know what the original function is, but because of the nature of the derivative, we're going to assume that it was a polynomial, since we know we could multiply the derivative, or the second derivative here, out to a polynomial function. So let's use 0, let's use 2, let's use 4, and let's use 6. So all of those numbers should be in the domain of the original function. All right, then we're going to test those values into the second derivative. If we're trying to deal with a question that asks about concavity, that specifically refers back to a second derivative. Okay, so always connect concavity with a second derivative. So these test values that I'm picking, I'm going to test into the second derivative. So I'm going to evaluate second derivative at 0. And all I care about here is the sign. So if I do 0 minus 1, 0 minus 3, 0 minus 5, that'll give me 3 negatives all being multiplied together. 3 negatives being multiplied is going to result in negative. What's that going to mean? If this is negative, then it turns out that my concavity is downward. Okay? Now on here and on a test, I'd want you to be careful. If you're doing something that has to do with increasing, decreasing, and you have a negative, you would do this symbol to indicate that you are decreasing. But if you're doing something that has to do with a second derivative has to do with concavity, then you're going to use this cup downward symbol to indicate that's the behavior there. All right, f double prime at 2. So there we'll do 2 minus 1. And then we'll do 2 minus 3. And then 2 minus 5. And then we want to determine just the signs of those values. 2 minus 1, that's going to be positive. 2 minus 3, that's going to end up being negative. And then 2 minus 5 is also negative. This is a positive multiplied by 2 negatives. That's going to end up being positive. So we're going to put a positive sign down here because we're dealing with second derivative that's telling me about concavity. In that situation, I am concaved upward. All right, let's now do second derivative at 4. And so on that one, we'll have the 4 minus the 1. We'll have 4 minus 3. And then 4 minus 5. And so there, it looks like the first one's going to be positive. The second one's going to be positive. But the last one's going to be negative. And then that's going to make it negative overall. So there, it's negative. That means we're concaved downward. Okay, and then finally do 6. And it looks like on all of those, we're going to have a positive. So having a positive on all of those is going to result in a positive overall, and that's going to indicate we're concaved upward. All right, so on this one, it was asking where's the graph concaved up or downward? And so from here, we're ready to give our answer. I'm going to start with concaved upward. So concaved up. We always want to give these as open x intervals. We're always here looking at these numbers that we had found from setting the second derivative to 0 or finding where it's undefined. So in answering this question, where is it concaved upward? It looks like between 1 and 3, it's concaved upward. So from 1 to 3, and then union also to the right of 5. So that would be from 5 to infinity. All right, and then concave downward. On this one, concave downward look like from the left of -1. So that would be negative infinity. I'm sorry, not -1, +1, to the left of +1. And then union also looks like between 3 and 5. Okay, so on that one, these two are what they're looking for their final answers. All right, this guy here, it starts us from the beginning of the problem. It says, hey, where is this function concave down? This is nice in that they're not asking for both, they're just asking for one. Let's see what happens on this particular function. This may be something interesting here. So if we take the first derivative, so we're seeing this, and that's ultimately going to mean go to the second derivative. If we take the first derivative here, we get 10x plus 2. Then if I take the second derivative, notice that I get a constant function. I get 10. What in the world does that mean? On this particular type of function, if you get a constant for your second derivative, that indicates whatever sign that constant is. So here we see that this sign is positive. That's going to indicate that this function is concaved upward if you get a positive, downward if you get a negative at this point. But this one, it would be concaved upward for all of its domain. We notice that this particular function has a domain that would be all real numbers, negative infinity to positive infinity, since we have a polynomial type thing here. So this one is asking where it's concave down. Well, this one's never concave down because it looks like it's concaved up over all real numbers. So we're going to say here concaved up on negative infinity to infinity, which means this one is not concave down. For any number. So you could just say not concaved down and you'd be good for an answer there. Okay, I did want to show you that one because it was kind of an interesting question. I didn't want you to think that you were doing something wrong if you ran across a question like that and there was actually not a solution because it's not concaved downward at any point. You can think of that would make sense. Like if you were going to go back and look at the graph of that function, we know that function is going to be a parabola. And we can see there from the highest power on the x that would be true. It would be concaved up because the value in front of the x squared is positive. So it totally makes sense that this would be concave downward nowhere. All right, this particular problem is kind of a, I'm going to say, go from the very beginning and answer all kinds of information kind of problem. There's my function. Y'all see it's a product combined with a power, looks like. And then down here, it's asking for multiple things. Domain, critical numbers, where is it increasing, where is it decreasing, if it has any kind of local max or min, inflection points, concavity, as far as that's concerned. So what we're going to do is just take this one from the top, so to speak, and find out as much about it as we possibly can. So the first thing here is talking about the domain. This function, if you were to square out that x minus 3, you'd have to FOIL it out. You'd have to run through that negative x. This is a polynomial for all practical purposes, even though it's not multiplied out, but that's going to indicate that my domain is going to be all real numbers. So I do want to make that note. All right, from here, I want to find the first derivative. So to do critical numbers and things like that, the first derivative is what I want. Okay, there's two different ways that we can think about this problem. If you'd like to FOIL out the x minus 3 all squared and then run through the negative x, that would be totally fine. If you'd like to leave it as it was and treat it as a product and kind of a chain wrapped up in there, you can do that as well. I'm actually going to do that just so that you can see and have the experience of doing it that way for future reference. So f prime of x, I'm going to treat this like a product. The only thing I'm going to do, though, is I'm going to separate out that negative sign and say the negative does not have to be considered in the actual product rule, I can just leave it as a -1 sitting in the front. Okay, now product rule says I'm going to keep the first, so I'm going to keep the x, and then I'm going to take the derivative of the second. The second part's the one I'm going to have to use the chain rule on, so I would multiply the power to the front. I would keep the x minus 3. I would reduce the power of 2 to an understood 1, and then I would then say take the derivative of the inside part, which would be 1. Okay, and then plus in the product rule, it says keep the second, which is the x minus 3 all squared, and then take the derivative of the first. Derivative of x is just 1, so there's that part. So it ends up being a pretty easy thing to do as far as a product rule followed by a chain rule type of deal. Now from here we want to try to factor this as much as we can. And it's already, I'm going to say in some ways factored. We notice on the inside here we have a couple of x minus 3 factors that are common. So I'm going to pull that out here in the front with this -1 that I already have. So -1, I'm going to pull out a single factor of x minus 3. Okay, then see what that leaves me with on the inside. Here I'd have an x times a 2 times a 1, so that's just a 2x. And then over here I would have a 1 multiplied by a single factor of x minus 3, which is just the same thing as a x minus 3. And then there in the middle we had a plus, so we didn't have to worry about any kind of signs. Now we can simplify that by just combining like terms. So we have -1, we have the x minus 3, and then here I'm going to change this to parentheses. At this point there's no reason for brackets, and this would be a 3x minus a 3. Now we notice that that 3x minus 3 also has a factor shared, and that'd be a factor of 3. I'm going to go ahead and pull that out. If I pulled that 3 out, I'm going to multiply it by this -1 we have in the front, so we'd have a -3. We'd have an x minus 3, and then this would become an x minus 1 when you factored that 3 out. All right, now that's the simplest form for the first derivative. Okay, as far as finding critical numbers, on here, critical numbers for this are going to be found either by setting the derivative equal to 0 or setting the derivative as something that would be undefined. On this one, you are not going to have that situation of having an undefined derivative, since my derivative is a polynomial. Critical numbers here, this -3 doesn't have an x with it, so I'm not going to yield anything from that. I'm going to get something from the x minus 3. That'll give me a critical number of x is 3. And then the x minus 1 would yield a critical number of x equals 1. Okay. So from here, what I'm going to do is go ahead and work on increasing, decreasing. So for increasing, decreasing, I put my critical numbers for my first derivative on a number line. Put them in order. So there I've got a +1, and then I've got a +3. And I'll just dot these off. This is not being asymptotes, it's just reference here. All right, and then I'm going to pick some test values. Let's say I pick 0 over here. Something between 1 and 3 that's nice. Let's say it's 2. Something to the right of 3. Let's say 4. If you ever get into the situation where you need to choose something between, let's say, 1 and 2. Between 1 and 2, you could choose 1.5 or 1.5, and then you could use your calculator to determine the sign of your derivative. So don't feel like these always have to be whole number values. They could be something that's fractional. All right, and from here, we're going to take and plug those test values into our first derivative. I'm going to go ahead and put some notation, say, hey, remember that was our first derivative. Okay, and I'm going to kind of quickly do these. We've done these before, so f prime at 0, I'm plugging in. I'm just going to kind of eyeball these. The -3 up here is definitely negative. If I plug in 0, I'm going to have 0 minus 3. That's going to be negative. And then plugging in 0, I'll have 0 minus 1. That will be negative as well. 3 negatives would be negative overall. At this point, it would tell me my function's decreasing, so going downward. F prime at 2. I'm looking back at my derivative and plugging in 2. The -3 in the front's negative no matter what. Okay, plugging in plugging in +2, 2 minus 3, that's negative. And then plugging in 2 to the third factor, 2 minus 1, that's positive. So in this one, I have 2 negatives multiplied by a positive. That's going to be positive. That's going to indicate that I'm increasing, going uphill. All right, f prime at 4. So the first negative number in my derivative is negative no matter what. 4 minus 3, that's going to be positive. And then 4 minus 1, that's also going to be positive. So I have a negative multiplied by 2 positives. That's going to be negative. So negative there, indicating I am decreasing. So what you have to be careful of is when we get to this section, we're now dealing with all the derivatives that we're going to look at. We're dealing with a first derivative to tell us about increasing, decreasing behavior, and also relative max and mins. And then eventually we're going to be looking at the second derivative, but the second derivative is specifically going to be telling me about concavity and possible points of inflection. So we really have to keep these things separate. And what I'm actually going to do here is I'm going to kind of draw a line down through here of, hey, all of this had to do with specifically a first derivative. All right, from here, we can tell from the graph of my number line here that it looks like we have some relative max or mins. It looks like the value 1 here is going to be a relative min. And then it looks like the value 3 here is going to be a relative max based on the behavior around it, what's going on with it. All right, so let's go ahead and find those min and max values. And remember here, it's always found by going back and evaluating the original function at these numbers I have highlighted in yellow. Okay, so for my relative min, I want to evaluate f at 1. Okay, the original function back here, remember it was negative x multiplied by x minus 3 all squared. So it's going to be, in this case, negative 1 multiplied by, not x, but 1 minus 3 all squared. So that's going to end up being negative. And then 1 minus 3 is negative 2. And then when I square negative 2, it would become positive. But because I have this negative out in the front, we're going to end up with a negative 4. Okay, and I'm going to go ahead and come over here to the side and answer this question. We have a relative min of negative 4 when x is equal to 1. All right, we also had a relative max. That was going to occur when we evaluated the function at 3. So we'd have negative 3, and then here 3 minus 3 all squared. Negative 3 is going to remain negative 3 for now, but then 3 minus 3, that's 0. 0 squared, 0. Negative 3 times 0, 0. So we have a local max of 0 at x equals 3. All right, from here, let's see here. We can also go ahead and fill in domain. Domain we said was all real numbers. So negative infinity to infinity. Critical numbers, we said those were x equals 3 and x equals 1. Okay, increasing, decreasing, we can go ahead and do that. We said we would be, looks like increasing from 1 to 3. Remember, these are open intervals of x. And then decreasing looks like from negative infinity all the way up to 1. And then union, decreasing also from 3 to infinity. And remember, on both of these, we're looking back over here at our number line test and looking at the behavior we said would happen there. And then you see the only thing that leaves me now with is inflection points and then concaved up and concave down. On here, for that, I need to find a second derivative. So I'm going to switch over and say now, second derivative is going to be found from looking at the first derivative. So I'm going to kind of draw an arrow over. The one thing I'm going to do is I'm going to separate that negative 3 out as a constant. So I'm going to say f double prime of x is going to equal the negative 3. I'm going to leave where it is. And then on the inside, I'm going to be having to do product rule. So we've got the product of the x minus 3 and the x minus 1, if I choose to leave it like that. And what I could do is multiply that out and then just take derivatives of that as a polynomial. That might be easier. I'm going to go ahead and use product rule just because I'm on a roll here. So keep the first, derivative of the second is just going to be 1 plus, keep the second, derivative of the first is going to be 1. So this is a pretty easy product rule kind of deal. So I'm going to keep that negative 3 out. And at this time, because I'm just multiplying by 1s, I really just have an x minus a 3, and then plus an x minus a 1. And so that's going to reduce to -3. We can do parentheses at this point. You don't need the brackets. We've got an x plus an x, so that's 2x. And then a -3 minus 1, so that's -4. And then I have a factor of 2 in common to both of those. That 2 would be multiplied by the -3 on the outside. So I'd have -6, and then this would become an x minus a 2. All right, now we're looking for possible points of inflection. So on there, what we're going to do is look at where the second derivative is either 0 or where the second derivative is undefined. Okay, in this situation, the second derivative here is also polynomial, so this undefined case is irrelevant. We don't have to worry about that. Where the second derivative would be 0, we look at the second derivative function here. We have the -6 out in the front. It doesn't have an x with it. If it did, I'd want to make sure to set it to 0. It does not, though. The x minus 2, if I set that equal to 0, then we can see there I would get x is equal to 2 as a possible inflection point. All right, now from here, we're going to do another number line test, but this number line test is specifically done with the second derivative. So I'm going to come over here. There's only going to be one number on the number line test for this one, and that's that 2. I'm going to dot it off. I'm going to choose a number to the left and a number to the right. Okay, so let's say here we choose 0 on the left. Seems like a good number. And we choose 3 on the right. But the difference here is you take those and you plug those numbers into the second derivative. And the second derivative is going to give you the concavity. So if you have a positive value, that will say it's concaved up. If you get a negative value, it's concaved down. Okay, so I'm going to put a little note here and say into f double prime. So into f double prime, if I evaluate f double prime specifically at 0, I get a -6 and then a 0 minus 2. That gives me a negative multiplied by a negative, which is going to end up giving me a positive overall. So positive here, I'm not going to do an increasing motion, I'm going to do a concaved up motion. So that tells me about the concavity. All right, and then if I do f double prime at 3, that's going to give me -6 times 3 minus 2. That's going to give me a negative multiplied by a positive, which is negative overall. This negative here means that it's going to be concave downward. So now I can answer the question about concavity. This thing is concaved up, and we always, at this point, want to look at that number to tell concavity. Okay, so concaved up from -infinity all the way up to 2. This will also be an open x interval, and then concave down from 2 to infinity. Now, on prior pages, it said if the concavity changes from up to down or down to up, vice versa, basically if it changes, and 2 is a number that's in the domain, which in this case it definitely was, the domain was all real numbers, then there would mean there's a point of inflection at that value too. Okay, on here, to find your inflection point, once again, anything in yellow to actually find points, whether it be relative max or mins or points of inflection, you always go back to your original function to evaluate those. So for your point of inflection, you would go back and evaluate f, the regular function f, at 2 in this particular situation. So that'd be -2 and then times 2 minus 3 all squared. So that would be -2. 2 minus 3 is -1. When you square that, it would become positive, and then multiply by the -2 you have in the front. And on these, they are always ordered pairs. So actual point of inflection. So you're going to say the x value that I plugged in was 2, the y value that I got out was -2, so that would be my point of inflection. All right, so make sure you're able to do problems like this. I'm only giving you, at this point, one example as far as this is a polynomial type function. It was written as a product. kind of had to do a chain rule in there when we did derivatives, but you need to make sure that you understand and know how to do these particular problems. They're complex, they're involved because you're doing multiple things, but it's also in a way comforting in that some things that you do are similar. All right, what I'd like to do now is go to what's called the second derivative test. And this is where I'm going to say things can get slightly confusing as far as the name and what we've told you about second derivatives. In general, we have said, hey, second derivatives, that means you're going to be testing for concavity. Is it concave up? Is it concave down? That's what the second derivative tells us about. But there's a theorem that says if you have c being a critical number of f of x, so the c would be found by taking the first derivative and finding where the first derivative is either 0 or undefined. If you evaluate the second derivative at that critical number and you find out you have upward concavity at that critical number, that's going to indicate that you have a relative minimum. Essentially here, your c value would be down in here somewhere, and this is indicating if you have concave up behavior there, that's going to be a low number. Same thing, if you go back and you evaluate your second derivative at that critical number and you find out you have concave downward, that means that that critical number there is going to create a high point. So it tells you something about relative max and mins. If, in a third situation, your second derivative gives you 0, I'm going to say that's an unfortunate occasion of it yields no information. So you must use a first derivative test to determine any kind of relative extrema. So here's what I want you to know. The second derivative test, even though it has to do with the second derivative, and your second derivative is telling you about concavity, it's a test to determine if you have extrema, relative extrema. So this is a test for relative extrema. Make sure to put that in your notes. That way you don't get this mixed up with anything else. All right. And then here, the important thing is that c is a critical number of f of x. All right, so I want to run through this example with you and show you kind of all the possibilities of what this second derivative test indicates. And probably on an exam, I would either specify I want you to use the second derivative test, or I would give you information so that it would make the second derivative test the obvious option for this type of question. So this says find the critical numbers of f of x and then use the second derivative test where possible to decide if the critical numbers is a relative max or minimum. So all we're going to do here, we're actually not going to find the relative max or min, we're just going to indicate if we have one at the critical numbers. So first thing here, let's find the critical numbers of f of x. All right, so let's take the first derivative of this guy. So f prime of x, we would get negative 15 x to the fourth, and then plus 15 x squared. And then what we want to try to do is factor this as much as possible. We see that there's 15s in common. The first term is actually a negative 15, so we're going to factor out negative 15. Looks like the lowest power in x we have is squared, since there's x's in both. And then because we're factoring out a negative, this would become a positive x to the second. This would become a minus 1. And then we can factor one more time since the second group is a difference of squares. So that would give me two binomials, one with an x plus 1 and one with an x minus 1. All right, from here, we now want to try to find the critical numbers. So the critical numbers for the first derivative are found where the first derivative are either 0 or undefined. We're not going to have an undefined situation in this case since our first derivative is a polynomial. So our critical numbers here are going to be determined by these factors. We've got this one, and this one. Notice that that first factor does have an x in it, so you want to make sure to set it equal to 0. So negative 15x squared equals 0. X plus 1 is 0, or possibly x minus 1 is 0. We notice in the first one we have that negative 15. We also have the square on the x. Well, because all of that is being multiplied, and then I'm going to say the power, I'm going to say is somewhat irrelevant in the solving of that, then we're going to get that just x is equal to 0. On this one, we're going to get x is equal to negative 1. And on this one, we're going to get x is equal to 0. So those are the critical numbers. Now, to use the second derivative test, so we're going to go ahead and put a note and say, hey, we're doing the second derivative test. All right, to do that, we take these critical numbers and we plug them into the second derivative. Well, that means that we need to find the second derivative. Okay, now on this particular problem, we've not run into this yet in other questions, but on this particular problem, it is more convenient for me to use the first version here of my first derivative because it's nice and polynomial, it's all multiplied out, and that will be an easy place for me to take my second derivative from. So I want to do second derivative. There, I'm just going to be using power rule, so this would end up being negative 60 x to the third, and then plus 30 x. Now, I do want to go ahead and factor that result. So we could factor out a negative 30x, and then that would leave me with a 2x squared minus 1. Now the 2x squared minus 1 doesn't factor further in any kind of pretty way. It looks similar to difference of squares, but the 2 that we have as a coefficient in front of the x squared is not a perfect square, so we're not going to go anywhere further with that. Now what we're going to do is we're going to use the second derivative, and we're going to plug our critical numbers into the second derivative to see what the results yield. So we're going to evaluate the second derivative specifically at the critical numbers. So we're going to do it at 0 first. That'll be negative 30 multiplied by 0, and then multiplied by 2 times 0 squared minus 1. Well, negative 30 times 0 yields 0, and then if I multiply 0 by the other group of stuff, I will get 0. That means I'm going to get no information there. Okay, and that also further means that if I'm going to find out if that's our possible relative max or min, I'm going to have to go back and use the first derivative test. And the first derivative test is where I do a number line test. So we'll do that here in a little bit. All right, f double prime at negative 1. So there we have negative 30 times negative 1. And then 2 times negative 1 squared minus 1. And the only thing we care about here is the sign, as long as it's not equal to 0. So the negative 30, that's most definitely negative. The negative 1 is most definitely negative. And then if I do negative 1 squared, that's going to be positive 1, multiplied by 2, that's going to be 2, and then 2 minus 1 is going to be a positive. So I have 2 negatives multiplied by a positive, that's going to be positive. That's indicating that we're concaved upward at that critical number, which is going to make that critical number a minimum. So we're going to have a relative min when x is equal to and what was that value? Negative 1. Okay, and like I said, we're not actually going to find the relative min on this particular problem. We definitely could. If we were asked to find the minimum, we would now plug negative 1 back into the original function to find that y value. But on this particular problem, it did not indicate that we wanted to find it. Only indicated we wanted to tell which we would have, a min or a max. Okay, now we go to the positive 1. So we're evaluating the second derivative at the critical number 1. So there we'd have negative 30 multiplied by positive 1. That's multiplied by 2 times 1 squared minus 1. As long as it's not 0, all we're wanting to know is it negative or positive. The 30 is negative, the 1's positive, and we can see on the second group of stuff, if we evaluate, that would end up being positive as well. So we have a negative multiplied by 2 positives. That's going to yield a negative. That's going to mean that we're concave downward at this critical number, which means at that critical number, it's going to yield a relative maximum. So we'll say here we have a relative max when x is equal to positive 1. All right, so far we have this information that we want to box in, but we have one other piece we don't know about, and that is what happens at x equals 0. At x equals 0, our second derivative test is inconclusive, and so that being the case, we have to go back to the first derivative test, and that's somewhat inconvenient. One of the big reasons we use second derivative tests is sometimes it's just a whole lot easier. But I wanted to show you problems that involved, I'm going to say all scenarios. So one of the scenarios is what happens if the second derivative is 0. So then I revert back to something that I already know about. So let's go up here and let's do a first derivative test. So there we already have taken the first derivative. We've already found critical numbers. We specifically want to test around my critical number of 0. Now we've got to be careful there. So here's 0. I'm going to give myself a little bit of space. I also had critical numbers of 1 and -1. So I want to make sure, even though I've already identified what those are, I want to make sure that I include those on my number line, because when I'm testing and I'm choosing test values, I want to make sure that my test values are between critical numbers. So like here, I already know that -1 yielded me a relative min, and I knew that 1 yielded me a relative max. But when choosing my critical numbers to test 0, I specifically want to be careful. I need to choose something between -1 and 0. That sounds like it'd be something like -0.5. Okay, and if you want to do -0.5, you could definitely do that. This would possibly be 1/2. Okay, and then I'm plugging those values back into my first derivative. Okay, and there I'm only wanting to determine the signs. So the first derivative evaluated at -1/2, that's going to be a -15 times -1/2 squared, and then -1/2 plus 1, and then -1/2 minus 1. Now, I'm okay with you using your calculator. If you want to type all that in your calculator and find out what the sign is, that's fine. If you do that, make sure you use parentheses exactly the way we're using parentheses here. But on this one, we can do this in our heads. -15, that's negative. When I square -1/2, that's going to end up being positive. When I do -1/2 plus 1, the 1's bigger, that's going to end up being positive. When I do -1/2 minus 1, that's going to be negative. So we have a negative, 2 negatives and 2 positives essentially multiplied together. That's going to result in a positive. So this being positive means I'm increasing on this side. Then I'm going to evaluate that first derivative at +1/2. Same idea here. So I'll have -15 and then 1/2 all squared, and then 1/2 plus 1, and then 1/2 minus 1. Okay, if I'm dealing on signs only, I don't really care about the numbers necessarily. Possibly on this one, I care about the numbers as far as like the 1/2 and the 1, which is bigger, which is smaller. This one's going to be negative. This one for sure positive since it's squared. This one for sure positive since both numbers are positive. And then this one over here negative since the ones, I'm going to say the -1 is bigger. So 1/2 minus 1 would be a negative value. And then here I have 2 positives and 2 negatives being multiplied. That would be positive. So the behavior here positive, I'm increasing on that side. There's not a relative max or min at x is 0. Okay. If you want to go ahead and say that, that's probably a good idea. So we're going to say no relative extrema at x is 0. Okay. Now, the reason that there wasn't any relative extrema was because when we did the first derivative test, it yielded no change in behavior. Do be careful. There's, I'm going to say, a possibility here you might misunderstand and say, hey, because the second derivative test didn't yield any kind of IMBO, then I'm not going to have extrema there. That's not necessarily the case. It's just the case here that it ended up there was no change in behavior over the 0 when we did that first derivative test. All right. This particular question is, I'm going to say set up, I'm going to say somewhat conveniently so that it would hopefully gear you towards using a second derivative test to answer the question. This one says, give all the values of x where f of x has relative minimum if f prime is equal to this function and f double prime is equal to this other function. we can see, even though we don't know what f of x is, we could see it would be some type of polynomial function. So the domain would be all real numbers. So what we want to do here is, since we're given information already about the first derivative and the second derivative, it seems only natural to use the second derivative test. So I'm going to put that note, use second derivative test to answer this particular question. All right, so what we want to do there is we need to know the critical numbers for the first derivative. So critical numbers come from either where the first derivative is 0 or where it's undefined. Well, in this case, it would only be where the first derivative was 0. Since it's polynomial, there's not going to be any place where it's undefined. And so I need to solve that. That kind of looks ugly, but look at this for a second. You've got some x's in common, and then also you have a 2 in common. So if we factor out a 2x, that leaves us with a 16x squared, and then minus a 25. And then that is now further factorable since it's a difference of squares. So we have a 2x, and then this would be 2 binomials factored as difference of squares. So a 4x, and a 4x, and a 5, and a 5, one with a plus, one with a minus. All right, and then here, critical numbers, we're going to set each of these factors to 0. This one is going to yield x is 0. Setting this one to 0, when solving, that's going to yield x is equal to negative 5 over 4. And then this one to 0, and eventually solving is going to yield x is equal to positive 5 over 4. So there's our critical numbers now. Now for the second derivative test, we take these critical numbers and we stick them into the second derivative. So at this point, evaluate into the second derivative. All right, so our second derivative, that was the 96x squared minus 50 function. So we're first going to evaluate second derivative at 0. And remember here, we really only care about the sign of our answer. So we have 96 times 0 squared minus 50. All right, since that wasn't factored, we're probably going to want to go ahead and do the algebra here, or the arithmetic. 0 squared, 0, 96 times 0, 0, 0 minus 50 looks like negative 50. That indicates to me that at that critical number, we have downward cupping behavior, so we have concave down. So that means that x equals 0 is going to produce a relative maximum. Now, this particular problem, I believe, was asking where we had relative minimums. Okay, so it says give all the values of x where f of x has a relative minimum. So that's not going to be one of them. All right, now we evaluate f double prime at negative 5/4. And I would totally expect you on these to use your calculator. So at this point, do 96 multiplied by, and use parentheses in the proper way here so that you don't have negatives that get lost. Okay, and just plug that in your calculator and see what you get. On this one, when you plug it in, you get 100. That's going to indicate that you have upward cupping behavior. And upward cupping behavior is going to indicate, hey, we do have a minimum. Okay, so x equals, and on this one, what was the value? Negative 5/4 is going to produce a relative minimum. So we can go ahead and box that in as one of our answers, since it was wanting relative minimums here. Okay, and then one more. We have f double prime at positive 5/4. And once again, just stick that in your calculator. On this one, when you stick in your calculator, you'll get the same result as when we plugged in the negative, since you're squaring it. So you get 100. That's going to yield upward cupping behavior, which is going to yield a minimum. So on this one, we'll say, so x equals positive 5/4 produces a relative minimum as well. All right, and then box that in as our other answer. All right, from here, I believe we've got one other question as a follow-up. And what we're going to kind of do on this is we're going to cheat as much as possible in that they gave us the first derivative and the second derivative and the original function. And what I've kind of done here is this is a nice way to ask you a question without it taking you a bunch of time. And they want us to answer these following questions. So they want the domain, critical numbers, increasing, decreasing, local max and min, and points of inflection, concave up and down. So on here, we're going to kind of do this one quickly. The first thing, this is a rational function, so the domain will be everything except for where the denominator is 0. So on this particular function, domain would be everything except for -1, because that would make the bottom of this function 0. All right, critical numbers, that would come from the second derivative. So for here, it would come from the first derivative. Critical numbers would be where either the derivative is 0 or where it's undefined. 0, remember, is where the numerator is 0 in this situation. Well, the numerator doesn't have any x's in it, so the numerator will never be 0. So critical numbers in this situation would be where the derivative is undefined, which is going to be where the denominator is 0. So on this one, we kind of split off and say, hey, where's the numerator equal to 0? Well, that would be when 2 is equal to 0, and that didn't make any sense. So the other critical numbers would be found by saying, where is the denominator 0? Well, that would be where the x plus 1 all squared is 0, which could simplify down to where the x plus 1 was 0, which means where is x equal -1. Well, on this one, we can tell that we had a vertical asymptote of x equals -1. So -1 is not in the domain, so you have no critical numbers. Now, from here, you can still test increasing, decreasing behavior. And so on a number line, you would put your -1, make sure to denote that, hey, it's a vertical asymptote. And then you can test on either side of that -1. Let's say we test at -2, and we test at, let's say, 0. And we'd plug those values back into that first derivative. And so if we tested there, said first derivative at -2, that's going to yield 2 over -2 plus 1 all squared. Well, top's positive, bottom's positive, so overall it's positive. That's going to indicate to me that it's increasing in that interval. Okay, do the same thing at 0. So f prime at 0, we get 2 over 0 plus 1. Top's positive, bottom's positive, overall it's positive. So it's increasing there. So it looks like our behavior is all increasing. So let's come down below and answer some of these questions. Domain, we said that's everything but -1, because -1 was a vertical asymptote. Critical numbers, we didn't have any. The only one would have been -1, and it's not in the domain. Increasing, it looks like this function increasing everywhere except at that vertical asymptote. We need to make sure there to leave that out. So we're just going to say there we're increasing over the entire domain, -infinity to -1, and then union -1 to infinity. That means it's decreasing nowhere, and we're going to go ahead and give that as an answer. All right. Local max and min, we don't have any. We didn't have a change in behavior, and even if we had of, the only place that we're testing around is a vertical asymptote. The vertical asymptote can't possibly be a local max or min, so we'd say none on both of those. And then that leaves inflection points and concavity. So inflection points and concavity has to do with the second derivative specifically. We have the second derivative, it's already done for us. We would be looking at possible points of inflection. So on this one, points of inflection, those might occur where the derivative is either undefined or where it's 0. Well, it would be 0 if the numerator were 0. Well, in this situation, -4 would be 0. That doesn't make any sense, so that's out. Or it would be where the denominator was 0. On this one, we can see that would simplify to where is x plus 1 equal to 0. Well, that's where x is equal to -1. So if we're going to have a point of inflection, it would be at -1. Problem with -1 is it's a vertical asymptote. We know already we're not going to have a point of inflection because -1 is not in the domain of the function. So we can come down here and say we have none there because the only place it might have occurred is at a asymptote. Now we can still test concavity, and we're going to do a different number line. We're still putting, in this situation, the same number on a number line, but now we're testing for concavity. So let's do -2 and let's do 0, and you're plugging those numbers into the second derivative because you're testing for concavity. So we're going to do f double prime at -2. That's going to be -4 over. Now be careful on this one, it's a cube on the bottom. So we're going to have -2 plus 1 all cubed. The cube means that whatever value I get on the inside as far as a sign, we're going to remain with that sign because when you cube, you keep the sign of the inside answer. So we're going to have a negative on the top of this one. On the inside of this, notice we have -2 plus 1. That'll give us -1. -1 cubed would yield a negative. So we have a negative, divide by negative, that's going to end up being positive. So that's positive there. That would mean that I'm concaved upward in that region. And then if I evaluate f double prime at 0, I get -4 over 0 plus 1 all cubed. That'll be a negative. Looks like positive on the bottom of that one. So overall negative. Negative there means concaved downward. So we can answer now the question about concavity. Concaved up, and we got to make sure to go back and look at that number when we're talking about the concavity. So from -infinity, it looks like to that -1 would be concaved up, and then concave down from -1 to infinity. All right, y'all let me know if you have any kind of questions.